All right, we're back. We're on page 7, note 17, Calc C. We're talking about polar calculus. We're doing the calculus of polar curves. On page 6, we learned that there's a lot of derivatives, a lot of rates of change, right? We have dr d theta, which tells you what's happening relative to the origin. You're getting closer, you're getting farther away. We have dx d theta and dy d theta. Where do those come from? You rewrite your polar curve in parametric form, which is actually a really big deal. You do that a lot. So you rewrite your polar curve in parametrics, and then you have your dx d theta, dy d theta, same interpretations as dx dt, dy dt. So if they made sense to you when you're doing parametric, they still make sense to you. Dy dx, you just take dy d theta and divide by dx d theta. That's the slope of the tangent line. So the slope of the tangent line to a polar curve has y's and x's in it, even though the polar curve itself doesn't really have y's and x's in it. That's because they live in the xy plane. You just think of each point differently. You think like, how far am I from the origin and how far did I rotate? Just another way of looking at the world. So we had this like really general formula that we arrived at up here. We have said multiple times when we are graphing. So let's say here, where are you? So when graphing, we keep saying r of, I don't know, like r of t equals 0 gives the tangent lines at the origin, right? So we dot in the tangent lines. And I've been saying like those are the tangent lines, and you've probably been just accepting it for like multiple years at this point. We now know enough to actually show that those are the tangent lines, right? So that's what we're going to do here. So when r is equal to 0, so if you have a rectangular graph, this is your rectangular that you're going to turn into a polar. So it's like, what are you doing? Why would you auto shape my r? Here, here. Let's say something like this, right? Boom, boom. These right here are when r is equal to 0. Those are going to be your tangent lines. You're going to dot those in. They give you shape. What we want to do, and those are theta values. So what we want to do is we want to figure out why is it that those are the tangent lines. So to do that, we need a couple of things. We need to assume that, well, we don't need to assume this. We're going to assume this. We're going to assume that r is equal to 0 when theta is equal to alpha. So there's like some that maybe alpha is pi over 6, right? Every time you do r of pi over 6, you're going to get 0. Why would that make our equation drop out as just a tangent line? Like why does that give us a tangent line? Well, take a look what happens to dy dx when r is equal to 0. R equals 0 means that f of theta is 0. So I don't know why I wrote it as r equals 0. It would have been clearer if I had not done that, but I did it. R equals 0 is the same as f of theta, f of alpha, I guess, really. F of alpha equals 0. So if I go, I'm using that general form, and so I have f prime of alpha, sine of alpha. I have, this is f of alpha, but f of alpha is just 0, cosine of alpha. F prime of alpha, cosine of alpha. This is f of alpha again, and then sine of alpha. So let me actually, I'm going to write in that this is f of alpha, but f of alpha equals 0. Let me just write that in for a little bit of clarity. So what happens? Well, this part is going to cancel out because of the zeros. So let's do that. That's gone. F prime over f prime is going to cancel. All that's left for us is sine over cosine. And then sine over cosine we know is tangent. So when you're at the origin, the slope of the curve is tangent of alpha. We're getting our tangent lines. And we're back, I guess. I don't know. I got a notification. I turned it off, and I guess that like put me somehow out of the app. I don't really know how that would work. So we get tangent of alpha. So that means that the tangent line itself is actually just theta equals alpha, because the equation of a polar line through the origin is theta equals alpha. So if we are, what should I graph? I'm going to try to graph one of these. I don't know. Right, so this would be This would be theta equals like alpha 1. And then if you're following this in order, it'd be like alpha 1, alpha 2. So theta equals alpha 2. So our tangent lines are theta equals alpha 1, theta equals alpha 2. But then if we want the rectangular version of that, it's going to be y equals the tangent of alpha 1 x, y equals the tangent of alpha 2 times x. So at the origin, we are definitely getting the tangent lines. That's like, I mean, I've been saying it for like probably years, if you've been following my videos or if you've been in my class. But now we can prove it. All right, let's see if we can do this. Find the equation of the tangent lines at the origin for r equals 3 cosine of 2 theta. So here's the thing. We don't really need to do calculus on this. Like, I want r equals 3 cosine of 2 theta. Well, okay, so I just need to know when that equals 0. I'm going to start with a graph anyway, a rectangular graph. This is going to be a rose curve with 4 petals because 2 is even, so you double it. You know, period is pi, so 3, -3. So this is why we're doing calculus, but we've known how to do this basically since we first met polar, which is good because the more you know. Do you guys remember those? The more you know, it was like, I want to say it was like NBC ad campaign where they would tell you like some little life fact or whatever, and you'd be like, oh yeah, the more you know. All right, so what do we got here? Pi over, that's not even right. This is pi over 2. So pi over 4. So when r is 0, we get theta equals pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. Now, a sort of interesting thing is happening here, though. So think about your polar curves. When you plot theta equals pi over 4 and theta equals 5 pi over 4, these are really the same line. They're the same radial line if you allow them to have positive and negative r values. And then the same is true here, 3 pi over 4 and 7 pi over 4, the same radial line if you allow that. So the equation, the polar equations, so the polar tangent lines, and we could have, you could solve it sort of algebraically, kind of, I guess. Like r equals 0 gives me cosine of 2 theta equals 0. So then 2 theta is going to be pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Because I always like to solve between 0 and 2 pi, and then divide by 4. Nope, then divide by 2, and you'll get a 4 denominator. 4 in the, whatever, 4 in the denominator. So I'm going to say this, theta equals 3 pi over 4. So the polar representation, you have like multiple representations of the angle. If I convert them though, so I'm going to say in rectangular tangent lines, my stomach just growled really loudly. I don't know if the mic picked it up. I wouldn't be surprised. It's y equals the tangent of pi over 4 times x, but the tangent of pi over 4 is 1, so y equals x. And then it's y equals the tangent of 3 pi over 4 x, but the tangent of 3 pi over 4 is -1. Now, if I had used 5 pi over 4, the tangent of 5 pi over 4 is also 1, so you only get the one rectangular representation. There's an infinite number of representations of the polar line. There's only one for rectangular. So these would be my answers. I'm going to stop here, I guess. I'm going to stop here, come back in the next one, and finish the next problem, even though I think that my timing is probably way off on these videos. But we'll see. So see you there.